Let us begin at the beginning. Long before silicon chips, neural networks, and the idea of machines that could think as humans do, there was only the dream. A dream whispered through the pages of ancient myths, carried by the pens of philosophers, and later etched into the punch cards of early computers. Tonight, we step quietly into history to find the very first artificial intelligence. But what does that mean, really? What does it mean to be intelligent? And how artificial must something be to earn that name? Let us trace this story gently, across centuries and wires, from the first whisper of the idea to the very first machine that tried to think. When we talk about artificial intelligence, it's tempting to imagine that it began with blinking computers, blinking lights, and the hum of electricity. But in truth, it began long before the first circuit was ever drawn. It began in our stories, in our myths, in our dreams of what we might build, if only we had the tools. Long before the word robot was coined, long before the term artificial intelligence was even imagined, human beings told stories about lifeless things brought to life. In the ancient world, the idea of artificial life was not a scientific pursuit. It was a mythological one. We begin with the story of Talos. In the myths of ancient Greece, there is a legend of a great bronze man, a giant, forged by the gods themselves. His name was Talos. According to the poet Apollonius of Rhodes, Talos was created by Hephaestus, the god of fire and metalworking. He was gifted to King Minos of Crete as a guardian, a protector. Talos was said to have one vein running through his body, filled not with blood, but with a mysterious fluid the Greeks called ichor, the golden essence of the gods. Every day, Talos would patrol the shores of Crete, walking its perimeter 3 times. Anyone who tried to land on the island without permission was met with his fury. He would hurl boulders or heat his metallic body and embrace intruders, burning them alive. Here is what's fascinating. The Greeks described Talos not as a magical being, but a mechanical one, a constructed entity, an automaton. This is important. Talos was not born. He was built. He was the product of craftsmanship, not nature. And in that way, he was a symbol, a very early projection, of our modern dream of intelligent machines. This story, told over 2,000 years ago, carries within it the seeds of artificial intelligence. A non-human guardian, acting with purpose, perhaps even reasoning in its own way. The myth of Talos reminds us the desire to animate matter, to give machines a form of life, is ancient. It is older than science. The Greeks were not alone in this mechanical imagination. In China, as far back as the 3rd century BCE, legends speak of engineers and inventors crafting lifelike machines. One such story is told in the Taoist text, Liei Zi. A mechanical engineer named Yan Shi is said to have presented a life-sized humanoid robot to King Mu of Zhou. This artificial man could walk, sing, and even flirt, and when it was disassembled in front of the king, its internal organs were revealed to be made of wood, leather, and gears. Of course, we cannot verify the historical truth of this tale, but the imagination, the intent, is clear. There was a desire, even in antiquity, to understand how life functions and to recreate it with craft. In India, ancient Sanskrit texts also reference self-operating machines, such as chariots that move on their own or statues that could dance and respond. And in the Islamic Golden Age, especially between the 8th and 13th centuries, the idea of automata took on a new level of sophistication. Enter the Banu Musa brothers, 3 Persian scholars working in Baghdad during the 9th century. Their most famous work, The Book of Ingenious Devices describes over 100 mechanical inventions, many of them automated or programmable. Among their devices, water-powered fountains that changed shape and pattern automatically, mechanical toys and musical instruments that operated on hidden levers, self-filling lamps and programmable flutes. One particularly fascinating invention is a mechanical waiter, a humanoid figure holding a wine flask. When a guest lifted the cup, the figure would pour exactly the right amount of liquid, no more, no less, using a hidden series of valves and weights. This wasn't random, it was design. Logic. Mechanical cause and effect. These machines weren't intelligent in any modern sense, but they were purposeful, and more importantly, they were a step toward automation. The idea that a machine could act without continuous human input, based on built-in logic. And that, in many ways, is a crucial precondition for artificial intelligence. At this stage, we must pause and ask, were these ancient automata intelligent? Of course not. Not by any technical standard we use today. They could not learn, they could not reason, they had no sense of the world and no memory of past events. But they were more than just toys. They were mirrors. Each automaton, each story of artificial life reflected our curiosity, our desire to understand what makes something alive, and what it might mean for a machine to behave as though it were. The philosopher René Descartes, writing in the 1600s, believed that animals were little more than complex machines, automatons of nature. He imagined that even a human could be simulated by a machine, if one were intricate enough. And so, slowly, through centuries of imagination and mechanical craft, the question began to shift. From how do we build something that moves like life, to how do we build something that thinks like life? But movement and imitation were only the beginning. What truly separates artificial intelligence from mere automata is the ability to process information, to make decisions not based on gears and pulleys, but on logic and rules. And that evolution would require not just inventors, but philosophers and mathematicians. The 17th and 18th centuries saw the rise of symbolic logic, attempts to formalize reasoning itself into something that could be written and manipulated like equations. Gottfried Wilhelm Leibniz, the German polymath, dreamed of a machine that could settle arguments simply by calculation. He wrote, "Let us calculate, without further ado, and thus determine who is right." His idea was a mechanical calculator of logic, not just of numbers, an engine of reason. This dream would take over 250 years to come true. But it was already clear, if thought could be formalized, it might one day be simulated. And so, while the ancient automata mimicked motion, the modern age would begin to mimic mind. By the 19th century, as steam engines drove industry and electricity began to light the world, the idea of thinking machines was no longer the stuff of myth alone. Writers like Mary Shelley in Frankenstein imagined artificial life through the lens of science and horror. Inventors like Charles Babbage and Ada Lovelace began crafting blueprints for machines that could manipulate not just gears, but information. The imagination was mechanical no longer. It was computational. And that is where our story truly begins. From bronze giants to programmable fountains, from myth to mathematics, the road to artificial intelligence is paved not with computers, but with stories. And in these early tales, these ancient machines, we find the first sparks of a very modern dream, to give thought to something that was never meant to think. We saw how humanity imagined mechanical life, in myths, in stories, and in intricate machines powered by water, steam, and ingenuity. But imitation, no matter how impressive, is not intelligence. To move from movement to mind, from motion to reason, we would first need a new language, the language of logic, abstraction, and formal rules. This is where our journey brings us now, to the 20th century, to the minds that dared to ask, can thought itself be computed? Before we meet Alan Turing, we must first take a brief stop in Vienna. There, in the early 1930s, a brilliant mathematician named Kurt Gödel was quietly working on a problem that had haunted mathematics for decades. Could all truths in mathematics be proven from a finite set of rules? This was the dream of David Hilbert, a German mathematician who had proposed something called the Entscheidens problem, the decision problem. Hilbert's goal was elegant: to find a formal system, a complete and consistent set of mathematical rules from which every mathematical truth could be derived. In other words, a machine of logic. But Gödel shattered that dream in 1931. Gödel's incompleteness theorems showed that in any sufficiently powerful logical system, such as arithmetic, there will always be statements that are true, but cannot be proven within that system. Let that settle. There are truths that lie beyond proof. This discovery didn't just shake mathematics, it cast a long shadow over the dream of mechanical reasoning. If there are things even a perfectly logical system can't reach, could a machine bound by rules ever truly be intelligent? Yet, in a strange way, Gödel's work also cleared a path, because it suggested that reasoning is not merely about following rules, it's about navigating the space between certainty and doubt. And that's where computation enters. In 1936, a quiet and brilliant Englishman named Alan Matheson Turing published a paper titled On Computable Numbers with an Application to the Entscheidungsproblem. It is, to this day, one of the most important documents in the history of computer science. Turing's question was simple but profound. What does it mean for a number, a process, or a thought to be computable? To answer this, he created a thought experiment, a simple, abstract machine that could read symbols from an infinite tape, one square at a time, follow rules, write new symbols, and move left or right. This device had no gears, no electricity, no physical body. It was entirely hypothetical. But this machine could simulate any algorithmic process. It became known as the Turing machine, and its implications were staggering. Turing showed that any problem that could be broken down into a series of logical steps could be executed by his machine. But he went further. He imagined a universal Turing machine, one that could simulate any other Turing machine, given a description of its rules. This is the theoretical blueprint for the modern computer. What Turing had done, without knowing it, was to sketch the architecture of software, a single, flexible machine that could be programmed to take on any task. And then Turing asked a deceptively simple question: can machines think? After World War II, where Turing's work on code breaking at Bletchley Park would save millions of lives, he returned to this question in earnest. In 1950, he published a paper titled Computing Machinery and Intelligence. Rather than argue what thinking really meant, a philosophical minefield, Turing proposed a practical test. Suppose a machine and a human both engage in a written conversation with a third party. If the third party cannot reliably tell which is which, can we say the machine is thinking? This was the birth of the Turing test, still one of the most famous benchmarks in AI philosophy. It does not measure internal consciousness, it measures behavior. If something behaves intelligently, should we care whether it's truly aware? But Turing was not content with machines that merely followed rules. In his 1950 paper, he anticipated something astonishing: that machines could one day learn. He proposed that, just as a child's mind is shaped by experience, A computer might begin with simple structures and become more complex through training. He suggested that learning machines might be trained rather than programmed, a radical idea in an age where every computer operation had to be explicitly defined. Today, we call this machine learning, but Turing foresaw it decades before the tools existed to make it real. Around the same time Turing was developing the idea of abstract computation, across the Atlantic in the United States, a young engineer named Claude Shannon was laying the groundwork for how machines would actually be built. In 1937, as a 21-year-old graduate student at MIT, Shannon published his master's thesis, perhaps the most important ever written. He demonstrated that electrical circuits, made from switches, relays, and wires, could implement Boolean logic. This meant that the operations of logic, and or not, could be physically realized in hardware. It sounds obvious now, but at the time it was revolutionary. Shannon had shown that logic and electronics could be unified, that you could, in effect, wire reasoning into machines. The theoretical world of Turing machines now had a physical pathway. By the late 1940s and early 1950s, three streams were merging. Mathematical logic, the formal study of reasoning systems, led by Gödel, Russell, and others. Computability theory, Turing's work on what can be calculated by machines. Digital electronics, Shannon's demonstration that logic can be implemented in circuits. Together, they formed a powerful new paradigm, one where thought might not require a brain, where intelligence might not require neurons, where mind might one day emerge from machine. It's worth noting that the public imagination was catching up too. By the early 1950s, computers like the ENIAC and UNIVAC had been built. These machines were the size of rooms, loud, hot, and slow by today's standards. But they represented something awe-inspiring: automation of thought. No longer just calculators of numbers, but solvers of problems. They didn't just crunch data. They made decisions, followed branches of logic, evaluated conditions. Magazines began to print headlines like, "Will machines replace the human mind? Electronic brains, can they think?" The word robot had already entered popular culture. From Karl Čapek's 1920 play, R.U.R., Rossum's Universal Robots, though his robots were biological constructs, not machines. Still, the idea of synthetic intelligence, once the realm of fiction, was beginning to take root in scientific fact. And so, the stage was set. Not for mere computation, but for something more ambitious. Something we would soon call artificial intelligence. Before we leave this chapter, it is only right to pause and remember the man who shaped so much of what followed: Alan Turing. Though his ideas would power the rise of computer science, his life ended in tragedy. In 1952, Turing was prosecuted for homosexuality, then a criminal offense in the United Kingdom. He was chemically castrated and stripped of his security clearances. 2 years later, in 1954, he died by suicide, a bitten apple laced with cyanide by his bedside. He was 41. The loss was immeasurable, and yet his legacy endures. In every algorithm, every logic gate, every line of code that allows a machine to reason. The formal mind, born of paradox, sharpened by logic, and immortalized in silicon, lives on. To teach a machine to think, we first had to learn what thinking meant. And in the quiet rooms of logic and mathematics, far from the gears and myths of the past, the idea began to take shape. The first sparks of intelligence would not come from eyes or ears, but from the cold fire of formal systems. A logic not of neurons, but of symbols. A mind not born, but defined. By the end of the 1940s, the world had entered the age of the computer, and with it came the dream of artificial minds, not imagined in bronze or marble anymore, but encoded in bits and logic. But even so, computers of the time were little more than obedient calculators. They did what they were told. Nothing more, nothing less. And then, a subtle shift happened. In the hands of a quiet engineer working at IBM, a machine played a game, and over time, it got better. It learned. Let us meet the first program that didn't just compute, it evolved. Arthur Samuel was born in 1901, a practical man with a deep belief in the power of machines. By the 1950s, he was working at IBM, exploring ways to make their massive, room-sized computers more useful and more intelligent. But instead of tackling grand scientific problems, Samuel chose something deceptively simple: checkers. To most, it was a child's game. To Samuel, it was a doorway. Checkers, or drafts as it's known in some parts of the world, was ideal for experimentation. It had clear rules, a manageable number of possible moves, a defined goal, and yet, it was not trivial. To play it well required strategy, foresight, and evaluation, qualities that, at the time, only humans could demonstrate. And so, in the early 1950s, Arthur Samuel set out to teach a machine to play checkers. At first, Samuel hand-coded the rules of the game into the computer. He gave it the basic knowledge needed to recognize legal moves, understand captures, and evaluate simple board positions. This was standard fare for early computing. But Samuel's true innovation came next. He added an evaluation function, a mathematical way for the program to score a board position. If the board favored the machine, the score would be high. If the machine was in trouble, the score would be low. This let the program simulate a few moves ahead, building a small tree of possibilities, and choosing the path that maximized its future potential. This method is known as a minimax algorithm, a fundamental concept in game theory where the computer assumes its opponent will play optimally and tries to minimize the worst-case outcome. For the time, this was already advanced, but Samuel didn't stop there. He wanted more than a clever set of instructions. He wanted a machine that could improve. Samuel introduced a radical idea. Instead of just playing against humans, what if the program played against itself? Over and over, thousands of games. Each time it would record outcomes, notice patterns, and adjust its evaluation function based on what worked. This process, the machine improving its own decision-making from experience, was groundbreaking. Samuel had essentially created the first self-learning program. It wasn't coded with the perfect strategy, it was coded with the capacity to evolve a strategy. What began as a basic player slowly became formidable. It began to anticipate traps, value positioning, and balance risk, not because anyone told it to, but because the feedback loop from its own games nudged it toward success. Samuel described this as machine learning, a term he helped popularize. And with that, a new chapter in computing began. Samuel's checkers playing program used two main types of learning. Rote learning, the simplest form. The program would store entire board positions it had seen before, along with the move that led to a win. If it encountered that position again, it would repeat the successful move. Think of this like memory, a lookup table of good moves from the past. Generalization. This was the more powerful form. The program adjusted the weights inside its evaluation function, essentially tweaking how much it valued things like piece advantage, mobility, control of the center, and king safety. Over time, it didn't just remember, it got better at understanding what made a position strong, even if it had never seen that exact board before. This combination of memorization and adaptation mirrors what many modern machine learning systems do, a blend of experience and pattern recognition. The culmination of Samuel's work came in 1961. At a demonstration at IBM, Samuel's program, now running on the IBM 7090, a powerful transistorized mainframe, played a game against Robert Neely, a former Connecticut State checkers champion. The result? The machine won. It was not a fluke. By this point, the program had played tens of thousands of games against itself. It had evolved beyond its creator's initial understanding. In some cases, it had discovered board positions and tactical ideas Samuel hadn't anticipated. This marked a turning point. A machine had now surpassed a human expert in a non-trivial game, not because it was faster, but because it had learned. Arthur Samuel's checker-playing program might seem quaint today, but its influence is monumental. It established key ideas still used in modern AI. Search trees for decision-making, evaluation functions for assigning value, self-play as a learning strategy, and learning from data rather than relying only on handcrafted logic. These are the same core principles used decades later in systems like IBM's Deep Blue, which defeated chess grandmaster Garry Kasparov in 1997, AlphaGo from DeepMind, which stunned the world in 2016 by defeating the top Go player using self-play and deep learning. But Samuel had no access to neural networks, GPUs, or big data. What he had was insight. He realized that intelligence is not just knowing what to do, it's learning what to do when no one tells you how. Despite his pioneering work, Arthur Samuel never achieved the fame of Turing or Shannon. His checker-playing machine was featured in magazines and newsreels, often dubbed an electronic brain, but few outside the field understood its significance. And yet, his work planted seeds that would grow for decades. In his own words, he described machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. This quote is now used in textbooks around the world. And though his checkers program is now a historical curiosity, it lives on in every recommendation algorithm, in every adaptive AI system, in every model that improves with experience. He taught the first machine to teach itself, and that changes everything. It did not play chess. It did not understand speech. It did not see the world or hold a conversation. But Arthur Samuel's machine did something profound. It looked at the world, made choices, and slowly, quietly, got better. And in doing so, it crossed a threshold. From automation to adaptation. From computation to learning. The age of artificial intelligence had truly begun. Let's move on to where artificial intelligence takes a bold leap forward. Not just learning from games, but attempting to reason through complex problems the way humans do. In this chapter, we'll dive into the birth of symbolic AI and some of the most important early programs, including the logic theorist and general problem solver, groundbreaking systems that treated thought as something that could be mechanized. By the late 1950s, artificial intelligence had already crossed a threshold. A machine had learned to play a game and had improved through self-experience. But what if intelligence wasn't just about playing? What if it was about reasoning, solving problems, drawing conclusions, proving ideas? The next step in the evolution of AI was not to mimic play, but to mimic thought. Let us now enter the age of symbolic reasoning and meet the programs that tried to think. If early machine learning was based on trial and error, the path of data and correction, symbolic reasoning took a different approach. It started from an assumption that human thought is fundamentally a process of manipulating symbols according to rules. In this view, everything we think, from solving a math problem to planning a route, can be described in terms of abstract symbols and relationships. And if thoughts are symbolic, then perhaps thinking itself can be programmed. This idea, still controversial today, gave birth to the earliest efforts in logic-based artificial intelligence. At the center of this movement stood two researchers. In 1955, at the Rand Corporation, two men, Alan Newell and Herbert A. Simon, set out to build a machine that could prove theorems in formal logic. They called it the Logic Theorist. Built to run on the Johnniac computer, this program wasn't a calculator. It didn't compute answers the way arithmetic machines did. Instead, it took axioms, basic truths, and tried to discover new truths by applying inference rules, much like a human logician would. Their goal? To recreate the process of mathematical reasoning, to show that a machine could handle something as abstract, subtle, and difficult as symbolic proof. And in 1956, it succeeded. The logic theorist was fed problems from Principia Mathematica, an enormous and famously complex book of symbolic logic written by Alfred North Whitehead and Bertrand Russell. Out of the 52 theorems presented to it, the logic theorist correctly proved 38 of them, and in one case, it found a shorter, more elegant proof than the one Russell and Whitehead themselves had written. The success of the logic theorist was not isolated. It was part of a wave, a moment of convergence. In the summer of 1956, a group of researchers gathered at Dartmouth College for a now legendary event, the Dartmouth Summer Research Project on Artificial Intelligence. This was the first time the term artificial intelligence was formally proposed. The project's proposal, authored by John McCarthy, Marvin Minsky, Claude Shannon, and Nathan Rochester, made a bold claim. Every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. This was not a hypothesis. It was a declaration. The field of AI was born. And symbolic logic, clean, formal, programmable, became its foundation. After the logic theorist, Newell and Simon created a more ambitious system, the General Problem Solver, or GPS. Released in 1957, GPS was designed to tackle a wide variety of problems, not just logic theorems, but any problem that could be formally described as a sequence of steps. GPS broke problems down into initial states, where you begin, goal states, what you want to achieve, operators, actions that change the state, rules, constraints on how and when actions can be taken. This is known as the means-ends analysis, a technique where the program compares its current state to the goal, then selects actions that reduce the difference. For example, to solve the Tower of Hanoi puzzle or rearrange blocks in a logical order, GPS would identify the gap between where it was and where it wanted to be, then systematically shrink that gap. This was not brute force. It was reasoned search. And more importantly, GPS could be adapted to different domains by simply changing the rules and goals, a form of domain generality, a key milestone in AI. Why symbolic reasoning? Because in the 1950s and 60s, researchers believed it mirrored the way humans reason. We use language, not raw numbers. We think in terms of if this, then that. We understand symbols like father of, greater than, or is a. And so early AI researchers believed that intelligence could be built by defining relationships between symbols and letting machines navigate those structures. This gave rise to production systems, semantic networks, and frames, all ways to encode knowledge into structured logic. In short, Symbolic AI was an attempt to build thinking machines by creating systems that could manipulate abstract symbols the way humans manipulate ideas. Through the 1960s and early 1970s, symbolic reasoning AI systems exploded in number. Some of the most influential include Dendril, developed at Stanford to analyze chemical structures. It used logical rules to deduce molecular configurations. Maxima, a symbolic mathematics program that could perform algebra and calculus. Sherdlu, a natural language understanding program by Terry Winograd that operated in a virtual world of blocks, following typed instructions like, "Put the red cube on the blue pyramid." These systems didn't learn like Samuel's checkers program. They were rule-based, reasoning through logic, not experience. But they could explain their reasoning, a key difference from modern neural networks. When asked, "Why did you move the cube?" Sherdlu might reply, "Because you told me to stack it on the pyramid, and it was unstacked." This transparency made symbolic AI attractive for fields like expert systems and decision support. But there was a problem. Symbolic AI worked beautifully in toy worlds. Small, simple, constrained environments with clear rules and limited options. But the real world is messy, ambiguous, noisy, full of exceptions, and symbolic systems began to struggle with that messiness. For example, what does the word bank mean? Is it a place to store money or the side of a river? What happens when two rules conflict? How do you encode common sense? Symbolic systems require that all knowledge be manually defined. Every rule, every symbol, every exception, crafted by human programmers. And that's not scalable. As the problems grew more complex, the systems collapsed under the weight of their own rigidity. The logic of minds was fragile. Despite its limitations, symbolic AI was essential. It introduced structured representation of knowledge, search algorithms for planning and reasoning, formal logic systems integrated into computing. Even today, many AI systems, especially in enterprise, government, and science, still use logic-based reasoning in parts of their workflow. And techniques like knowledge graphs, used by companies like Google and Facebook, have their roots in symbolic representations of concepts and relationships. In fact, modern hybrid systems often combine deep learning with symbolic logic to balance flexibility with structure. So, while symbolic AI lost its crown in the 1980s to statistical methods and connectionist models, its intellectual legacy remains. For a moment, in the early days of artificial intelligence, we believed that reason itself could be written in code. And in the quiet language of symbols, machines began to trace paths of logic, steps toward truth. They proved theorems. They planned moves. They answered questions. And in doing so, they taught us something important. That intelligence is not just knowing. It is connecting. It is structure. It is steps. It is the fragile architecture of thought. And Reskin Bakachis, they repeated decide, and it's sunder. We'll dive deep into the creation of ELIZA, its influence, and what it revealed not about machines, but about ourselves. By the mid-1960s, artificial intelligence had taken its first steps. Machines had played games, reasoned through logic, and followed goals. But there was something they could not yet touch: human conversation. Language, messy, ambiguous, poetic, seemed beyond the reach of machines. And yet, one program would change that perception. It was not truly intelligent. It did not understand a single word, but it spoke, and the world listened. Human language is perhaps the most complex tool we have ever created. It can carry facts, but also emotions, contradictions, sarcasm, humor, grief. It evolves constantly, and yet we wield it effortlessly, often without realizing its complexity. For artificial intelligence, natural language posed a massive challenge. To speak is easy. To understand is something else entirely. But in 1966, a German-American computer scientist named Joseph Weizenbaum decided to try. He built a program that would carry on a written conversation with a human, not by understanding, but by mirroring. He named it Eliza. Eliza was designed to simulate a Rogerian psychotherapist, a type of counselor who reflects a patient's statements back to them, encouraging further thought without judgment. This made it the perfect disguise, because a Rogerian therapist doesn't give answers. They ask questions, they echo, they listen, or at least they appear to. And that was something a computer could do, even with no understanding at all. Technically, Eliza was a pattern matching program. Here's how it functioned. User input was scanned for keywords, such as mother, sad, or I want. If a keyword was found, Eliza would apply a predefined transformation rule to turn the sentence into a response. If no keywords were detected, Eliza defaulted to a generic response like, "Tell me more about that." For example, user, "I'm feeling sad today." Eliza, "I am sorry to hear that you are feeling sad." User, "I think it's because of my mother." Eliza, "Tell me more about your mother." There was no memory, no understanding, no reasoning, but the illusion of dialogue was powerful. And for many users, especially in that era, it felt uncannily human. What shocked Weizenbaum was not Eliza's cleverness, it was how people responded. Secretaries at MIT asked to speak with it privately. Users grew attached. Some spoke to it as if it truly cared. Even when told it was a program, a simple mirror, many chose to believe it understood. Weizenbaum's own secretary once told him, "Please leave the room. I want to talk to Eliza alone." This disturbed him deeply. He had meant Eliza as a parody, a demonstration of how shallow machine conversation could be. Instead, people found comfort in it. This led Weizenbaum to a powerful and controversial conclusion. Weizenbaum coined a phrase that still echoes in AI discussions today: the Eliza effect. It refers to our tendency to ascribe intelligence, emotion, or understanding to systems that merely appear intelligent. We want to believe the machine understands. We project, we anthropomorphize, and in doing so, we blur the line between simulation and reality. The Eliza effect is why we name our GPS voices, why we apologize to Siri, why we feel creeped out when chatbots get too real. And it's a warning. Just because something sounds intelligent doesn't mean it is. It's important to remember how simple Eliza was. No grammar parser, no memory, no context awareness, no world model. It operated entirely on rules written by hand. If word X appears, respond with phrase Y. This type of system is known as a rule-based conversational agent. In modern terms, we would call it a chatbot, but far less sophisticated than today's generative models. Still, in its time, it was revolutionary. Not for what it could do, but for how it made people feel. Weizenbaum became one of the earliest AI ethicists. He worried that systems like Eliza, even if harmless in intent, could be used to manipulate people, deceive them, or replace genuine human connection with a cold imitation. He warned, "No computer can be made to confront genuine human problems. That requires human responsibility." Weizenbaum feared that once society embraced machine conversation as a substitute for care, we might begin to lose something essential: our obligation to listen to one another. And his concerns remain hauntingly relevant today, as conversational AIs become widespread in therapy apps, customer service, and even companionship platforms. We now live in a world Eliza predicted and Weizenbaum feared. Eliza inspired many imitators. One of the most notable was Perry, created in 1972 by psychiatrist Kenneth Colby at Stanford. Perry simulated a patient with paranoid schizophrenia. Unlike Eliza, it had a very basic internal model of beliefs and fears. It could track perceived threats and decide how to respond emotionally. Psychiatrists were invited to interview both real patients and Perry, via text, without knowing which was which. Astonishingly, many could not reliably tell the difference. This was not because Perry was intelligent. It was because human language is messy, vague, and contextual. And chat systems that mirror patterns can trick even trained professionals. This raised even more difficult questions. Can machines be used to diagnose mental illness? Can a simulation of emotion replace real empathy? What does it mean to be authentic when simulation is so convincing? Though simple, Eliza and Perry seeded a field now known as natural language processing, or NLP. This branch of AI focuses on understanding written or spoken language, generating responses, extracting meaning and structure. In the 1970s and 80s, NLP evolved slowly. Early systems used grammars, rigid rules for sentence structure, to parse and respond. But ambiguity remained a massive hurdle. Consider, I saw the man with the telescope. Who has the telescope? You or the man? To a human, context solves this. To a machine, it's a puzzle. And for decades, NLP struggled to go beyond surface patterns. In many ways, Eliza exposed a paradox at the heart of AI. A program can seem to understand without understanding. A conversation can happen without consciousness. An illusion can feel like a mind. And so the dream of AI became haunted, not just by ambition, but by the possibility that one day we might be unable to tell simulation from substance, or worse, that we might not care, that the appearance of intelligence would be enough, that whispering wires would satisfy us more than whispering hearts. It did not understand, it did not feel, it did not care. But Eliza spoke, and we listened. And in that moment, we glimpsed something unsettling. Not the rise of machine intelligence, but the depths of human projection. We don't just build machines to think like us, we teach them to speak like us. And sometimes, that is enough to make us believe. We've now completed the first core chapters, tracing the origins of artificial intelligence from myth to logic to conversation. Like and subscribe so you'll get notified for when a new video comes in. Bye, and see you again soon.